Welcome to Lecture 2 with Math 130, Introduction to Computer Programming with Java, and this is part 1 of 2 videos entitled Hardware. Be ready to answer the following after watching both parts to Lecture 2 videos. Why do we even need to learn about hardware? What are the 2 major things that a computer can do? What are the major components of a computer system? What's a CPU, an ALU, and a RAM? And what is an address in memory? How many bits in a byte? Who was Alan Turing and why is he famous? Good software needs knowledge of hardware. So this is very important. If you want to be a good programmer, you have to have a little bit of knowledge about the inner workings of the hardware. So we're going to open up the hood just briefly and talk a little bit about hardware today. Once we start learning how to build algorithms and to think algorithmically, we're going to see as well that different algorithms have different costs or expenses. We also want to consider the expense or costs of doing something and better ways of finding a solution to different problems that are less expensive and more efficient. What this means is that in order to create programs that are less expensive, they need to use up less memory, require less processing power, and be more efficient. One example of that would be requiring less lines of code. But the program must still be able to give us a result or a good enough approximation that we want. In order to better understand these concepts of expense and efficiency for software, we're going to need to learn a little bit about hardware. So what does a computer do? Well, fundamentally, it can do 2 major things. The first thing it can do is perform calculations, 1 billion calculations per second. In fact, it's so fast that 2 operations in the same time light travels 1 foot. That's how fast it can compute. The second thing is a computer knows how to remember results because it has hundreds of gigabytes of storage. A typical machine can hold 1.5 million books of standard size. Well, what kinds of calculations? The ones that are built into the language and the ones that you're going to define as the programmer. Now, are simple calculations enough? And by simple, we mean basic things like adding or moving. If you were just going to search the World Wide Web, which a lot of you do via Google, say, there are 45 billion pages or so on the World Wide Web, which if you say there's approximately 1,000 words per page and it needs 10 operations per word to go find, then it's going to require 5.2 days to find something using simple operations. Let's give another example. Say you wanted to play a game of chess. There's an average of about 35 moves for game setting. If you want to look ahead, say 6 moves, there's going to be 1.8 billion boards to check, which means there's going to be about 100 operations per choice, say, and that would require 30 minutes to decide each move. Well, that'll take you too long to play a game. So, summary, good algorithm design is needed to accomplish these tasks. Do we have enough storage? What if we could just pre-compute information and look up the answer? So back to our chess game example, if you wanted to have a lookup table in your memory, the computer memory, you would need to have 10 to the 123rd power different possible games contained in that lookup table. But there's only 10 to the 80 power atoms in the observable universe, so it's not going to be a good idea. Are there limits? Despite its speed and size, a computer does have some limitations. There's still some problems that are still too complex for it. When I get in my car in the morning and I'm going to be driving to the campus here, I'd love to know the exact weather that we're going to have so I can know how to dress and so on. But that's still too complex for a computer to predict on all local scales. And also, cracking encryption schemes can be too complex. And also, there are some problems that have been proven to be fundamentally impossible to compute. One of them is known as the Turing halting problem. That's predicting whether a piece of code will always halt with an answer for any input. That's impossible to compute. Computers are machines. So the question is going to be, how do we capture a recipe in a mechanical process? And it turns out, if you study some computer history, there were two kinds of computers. The first was the fixed program computer. So an example of that is a handheld calculator that's not programmable. It's fixed. You can do certain operations like adding, subtracting, multiplying, and dividing, but you can't do anything else. Another fixed program computer on a much larger scale was Alan Turing's Bomb. And that was the crypto-analytical machine, which is shown in a picture on this slide here, designed during World War II to break German codes for the Enigma machine. And it was designed specifically for that process. It was also built out of devices you don't see anymore, like vacuum tubes and relays. The other type of capturing a recipe is in a stored program computer, and this is what we are more familiar with today, where the machine can store and execute different instructions, and you can change what those programs are. Let's go and talk a little bit more about Alan Turing and why he was so famous. There's something called the Turing Test, and this is really cool for those of you that are interested in machine learning and artificial intelligence. The Turing Test, which is defined by Alan Turing, he's considered the father of computer science, back in 1950 is the foundation for the philosophy of artificial intelligence, AI. The Turing Test is basically this. You want to see if the machine has the ability to exhibit intelligent behavior equivalent to that of a human. So he proposed that a human evaluator, which would be in another room basically, would judge conversations between him and another human and him and a machine. And the machine, of course, is designed to generate human-like responses. And the human evaluator, who's off in a different room, would be aware that one of the two partners in this conversation is a machine, but they all would be separated from one another. And the conversation would be limited to a text-only channel, such as keyboard or screen. And if the evaluator cannot reliably tell the machine from the human, the machine is said to pass the test. The test does not check the ability to give correct answers to questions, though. It's just how closely the computer can mimic or resemble those a human would give. And this test was introduced by Turing in his paper, Computing Machinery and Intelligence, while working at the University of Manchester. It opens with the words, "I propose to consider the question, can machines think? Because thinking is difficult to define." Turing chooses to replace the question by another. Turing's new question is, are there imaginable digital computers which would do well in the imitation game? And that was the name of a movie that featured Alan Turing, his part of his life, the imitation game. More on Alan Turing, the Turing Test and artificial intelligence. Alan Turing's 1950 paper laid out the general idea of the test, and he also laid out some specifics which he thought would be passed in about 50 years' time. Each judge had 5 minutes to talk to the machine, and the machines passed if more than 30% of the judges thought they were human. Well, it turns out this Turing test has been passed by a robot or chatbot named Eugene back in 2014, pretending to be a virtual 13-year-old boy. And this program, Eugene, was a Russian-designed program. But he was able to get the 33%, but that was because there were only 3 judges, and he was able to fool one of them. So robots still have a long way to go to pass this gold standard of modern Turing tests. And the Turing test competitions are still held, and they have been for more than 20 years, and strategies that robots employ have changed over time. And this diagram over here just shows you a little picture of you have a judge who's judging both a computer and a human in different rooms. Okay, now let's finally get to computer systems and hardware. This picture here shows different parts of hardware. Over here on the left, you have input devices. In the middle, you have the central processing unit and the RAM, and on the right, you have output devices. So your basic machine architecture, it falls into these categories here shown on this slide. You have the memory, And you have the control unit, which controls the program counter, and the ALU, which does all the primitive operations. And you also have some input, and the computer has some output. So computer hardware components are the physical pieces of the computer. So there's four major hardware components of a computer, and they are the CPU, central processing unit, main memory, secondary storage devices, and the input and output devices. Let's look at each of these in turn on the next video. So please go to the next video to watch part 2 of this lecture.